Hello guys, welcome back to the LearnRISC-V YouTube channel. And in this session, I'm gonna talk about the power management unit. Precisely, I would just discuss about a partial functionality of the power management unit. And so it's more common nowadays to save power. There are many different ways to save power in the core by changing the system clock frequency, changing the core clock frequency, and sometimes shutting down the peripherals. And what we are gonna see in this session is about how the power is saved or managed in RISC-V based FE310 core. So if you read the manual on about the clocks, there are a few ways. There are registers to control and manage the core and the peripheral clock frequency. So the lesser the clock speed, the lesser the power that would be consumed by the core. That's the most common or basic technique to save power. And it's quite interesting to learn about the power management unit PMU in FE310. So in this decade, this power island or voltage island have become predominant in the VLSI. So before, the PMU or power management unit and the core and the peripherals all would reside in one clock and one power or voltage island. In that case, the power can be saved only by reducing the clock speed to a certain extent and by shutting off a few peripherals and by adjusting the peripheral clock. However, after the evolution of this power or voltage island, so these PMUs, the power management unit, would reside in a block called always on or AON, which means that this block should be on all the time, whereas the MOFF are mostly off block, in which the core and peripherals would reside, can be completely shut off, or like the clock can be resetted and the power to this block can be cut off, resulting in an astronomical power savings. Okay, so this is the pictorial representation of the power and clock domain in FE310 based on the manual and based on what I understood. Okay, so if you see here, the trigger to put the core and the peripherals to sleep comes from the MOFF block. So you can see the direction of the arrow, which always comes from here. And once this sleep has been initiated, and if the sleep has been initiated successfully, then the only way to wake up the core, or only way to bring alive this MOFF block, is by the wake up trigger or the wake up sequence from the PMU, which resides in an always on block. So the main functionality of this power management unit is to take the MOFF block to sleep and wake it out of sleep. But what we are gonna see in this session is only about this first part, how the sleep is triggered in FE310. Okay. So as I said before, the PMU in FE310 resides in always on block, and those PMU memory map registers start with the offsets 0x 100 all the way through 0x14C. with the base address of the always on block base address, which is 0x1 followed by 7 zeros. So what are there in this PMU memory mapped registers are that the first 8 memory mapped registers contain the 8 instructions for wake up sequence, followed by 8 instructions of PMU sleep sequence, and the last 4 memory mapped registers correspond to a PMU interrupt enable and the PMU cause and the PMU sleep, and finally the PMU key. Okay, and we would see in this session we would see the PMU key, PMU sleep, and we would see little of the sleep sequence. Okay, and the wake up related registers would be covered in a separate video session. So first, so the PMU sleep memory map register, so writing any value into the PMU sleep would initiate a sleep sequence. I said writing any value into PMU sleep would initiate sleep sequence because it's not just one single step to put the core into sleep. It's like a sequence, because in the VLSI implementation there might be state machines that has to go through several states to reach the final sleep state. Okay, and the PMU key register is before you write any of those PMU related memory map registers, the PMU should be unlocked by writing this key into the PMU key register. So this is primarily to prevent spurious triggers of PMU sleep, to avoid that, to avoid this spurious PMU sleep invocations. This PMU key would prevent that from happening, because every time you want to write into a register, it has to be preceded by a write into this PMU key, and this is the fixed value or hard-coded value that should be written into the PMU to unlock. And so this is the default sleep. It's not up, it's like a default sleep sequence. So if you go back to the memory map register, so from 0x1 followed by 4 zeros and 120 all the way up to 13C. So these 8 memory map registers by default are after power on resets. Now I see this is the value which is present, and as per the manual as well, this is the, if you go to the PMU, and you should be able to see the default sleep sequence. I'm looking for, where is that? Register memory map. That's surprising. I remember seeing that somewhere. So that's the instruction format. Okay, so that default PMU wake up program is there, but yeah, here it is. Default PMU sleep sequence, sleep program. So in FE310, you have the flexibility to write your own sleep sequence, and or these instructions are, what does this value specify is given here. If you see the instruction format, enables and wake up course as well as instruction format. Yeah, so this is the PMU instruction format, and I have created this table right next to that. So for this value, or the value 2F0 at this memory address corresponding to the first instruction of the sleep, and when you expand it into bits, this is what it corresponds to. And the first 4 bits, or the first 4 lowest significant bits, correspond to the delay. That means when the sleep sequence, or when any value is written into the PMU sleep, after these many, this is a multiplier, so whatever the value here, if the value here is 10, then 2 to the power 10 cycles would be delayed. So this instruction, whatever you mention on rest of those bits, or this instruction, as per this instruction, would be initiated only after a delay of these many cycles. So that is the delay multiplier here. And the bit 4 and 5 correspond to 2 pinouts from the PMU or AON block. So if you go to the schematics, and you can see this is the FE310 SoC, and you see there are 2 pinouts. One is the PMU out 1 and another one is PMU out 0. And these values are the bits, the values corresponding to the bit 4 and 5 correspond to the value that would be put on those pins. And why is that and how to use, we will see very soon, because in this session, that is the so I have used one of that to understand, to confirm if the sleep has been initiated on my board. Okay, so that's the bits, bit position 4 and 5, and 6 is not mentioned. 7 and 8 is to reset the core and high frequency clock. Okay, and the 9th bit is to isolate, keep MOFF isolated from the AON. I'm not yet clear what would happen if you see here, this bit has been set in all the instructions here, but what would happen if it is unset, I'm not that clear. So now coming back to this sleep sequence, so this one, since there is no delay, this would be executed right away once a value is written into the PMU sleep. And since this bit position 4 and 5 is 1, that would be 1 on these 2 pins, and these 2 would be resetted, and it would be isolated. And the second instruction, again without any delay, it would come back to the same, so the same values on these 2, 4 and 5. So yeah, and the same. But as you go down 3, how many is, yeah, on the 3rd instruction and so on. So if you see here, in the 3rd, the PMU out 0, the bit position, it has become 1 0 here, and in the last 2 3 5 instructions, you can see that these 2 has been set as 0. Okay, so these 2 bits transit from 0 to 1, and after some time it goes down to 0. Okay, so this is again the same explanation for those bit positions of those instructions. And I would cover this wake up register, wake up cause register later. So this is nothing but when the PMU, or when the core wakes up, or when the PMU triggers and wake up, what has caused the PMU to wake up. So it can be either an power on reset or an RTC or a digital wake up. There is a button on the board to, or an external reset and a watchdog timer. So we will see elaborately in the when I discuss about the wake up functionality of the PMU. And this one is again like you can configure the PMU to allow which set of events to enable or to bring the PMU out of reset or bring the core out of reset. Okay, so now let's go to the schematics. So in the schematics, if you see the PMU1 is a wire named WF reset, and the PMU out 0 has been named VDD core EN. And if you go to next, so if you see here, that output has been connected to one of the enable signal or enable pin of this power regulator, I guess. And so if this is 1, then you would see the 1.8 volt on this out, and once this is disabled and the power 1.8 volt would be cut off. And so that's the core power. If you see 1V8, so 1V8 is I can even see in the manual, I guess, data sheet. Okay, yeah. So that's the core supply voltage 1.8, okay, and the PLL, so that would be cut off. Okay, so this is what I tried to achieve to confirm. I probed this WF reset pin or the PMU out 1 on resistor 20. If you go down and watch this. So you can probe this signal at resistor R20, and you don't even have to, either you can probe this, what is that, VDD underscore core EN. Either you want to probe here, or you can even see this LED. There's a LED connected to 1.8 volt that would go off if the sleep sequence has been initiated properly. Now let's jump into the code. So it's such a very small code. As you see, I have created an app directory and named it as PMU wake, but right now it triggers only to sleep. Maybe later I will add the code to wake the core. And at the very first, I have added I remember adding a delay, yeah. So this delay, so that it would allow me to set my scope and probe the signals. But the main code are only these. Very first, writing the key, PMU key, which is hard-coded value. So first write into the key to unlock the PMU, then setting the PMU interrupt enable to 0. That means that none other than power reset would bring the core out of sleep, and then again unblocking the PM to trigger the sleep. So writing any value into the PMU sleep register would trigger sleep. But by the time when it comes here, you can see the sleep would have been already initiated. So let's build the code now. So now I would record the scope signals for 30 seconds. That's the CLIE oscilloscope. So now I'm capturing those signals in the background. Now once I run here, so first you can see the core or the debugger lost the control of the core because the VDD 1.8 volt is cut off. And now if you see the signals, yeah, you can see that the WF reset is also triggered from 0 to 1 and 1 to 0 back. So we have come to the end of the session with the demonstration of the core being cut off, or the power supply 1.8 to the core would be cut off. That means that a lot of power can be saved, and the sleep should be triggered only when the core is not in use. And in the later video I would try to demonstrate the wake up sequence with RTC. Okay, so if you're interested in this RISC-V based videos, feel free to subscribe and click the like button. And also, if you have any questions, I highly recommend you to either put on the comment section, or you can even go ahead and create a issue in the GitHub repo, where you can see people have created a few issues, and whenever I find time I will try to help you out. Yeah, thank you.